Hello, let's talk about moles today. Moles a mole is a number. Very much like you know that a dozen is 12 of something. You might also know that a bolt of fabric means 100 yards of fabric. A ream of paper has 500 pieces of paper in it. One gross is a dozen, 12 times 12, 144. And one mole is 6.02 times 10 to the 23rd particles. If we wrote that out in not scientific notation, an extra zero on there, that is how many particles it would be. It's a lot of particles. Now, to understand how big that is, I have a video that we're going to watch. This song will stick in your head for a while. Just be prepared.
Or a spot on your chin that you gotta shave around. But there's another kind of mole of interest to me. That's the kind of mole they use in dentistry. A mole is a unit, have you heard? Containing 6 times 10 to the 23rd. That's a 6 with 23 zeros at the end. Much too big a number to comprehend. Now say you had a mole of pennies to distribute around the world. To each of the 5 billion grown-ups, boys and girls, there wouldn't be a single soul down and out of luck, 'cause everybody in the world would get $1 trillion. Or say you had a mole of paper and stacked it toward the sky. Paper's awful thin, but that pile would get so high, it'd reach up into outer space. In fact, I think it's fine. It'd go up to the moon and back 8 billion times. And the mole is a unit, or have you heard? 6 times 10 to the 23rd. That's a 6 with 23 zeros at the end. Much too big a number to comprehend. Now suppose a mold of marshmallows fell upon the planet. Over each square inch of land and sea, you think that you could stand it? That layer would be 12 miles high and, of course, block out the sun. We're talking close to 5 million trillion tons. Well, maybe we could save ourselves if we all started eating 1 marshmallow a second. Not 2, because that'd be cheating. With 5 billion people munching, how long do you think it'd take? 40 million years, and that's without a bathroom break. And the mole is a unit, or have you heard? Containing 6 times 10 to the 23rd. That's a 6 with 23 zeros at the end. Much too big a number to comprehend. Let's say you had a mole of atoms. Would the pile be immense? Should I say the answer now or leave you in suspense? Well, atoms are so very, very small, you understand. You could hold a mole of atoms in the palm of your hand. So shake a little sugar in the middle of your palm. Now you don't want to spill it, so try and stay calm. You hardly can imagine and barely realize there are more atoms in that sugar than stars up in the sky. And the mole is a unit, or have you heard? Containing 6 times 10 to the 23rd. That's a 6 with 23 zeros at the end. Much too big a number to comprehend.
All right. So you can see that that is a huge number. Moles, that should be a mole, has a value as 6.02 times 10 to the 23rd. We call it Avogadro's number after Amedeo Avogadro. Amedeo Avogadro was Italian, and he was the first chemist to realize that if you had equal volumes of gases at the same temperature, you would have the same number of particles. He didn't actually discover Avogadro's number. He got it named after him for his contributions. Okay? Avogadro's number was determined after Robert Millikan did his oil drop experiment. And the oil drop experiment is what was used to figure out the charge on one electron. Millikan did the oil drop experiment, and he was able to take the charge of the one electron and divide it into a charge of a Faraday of electrons, 1 mole of electrons, and that is where they came up with the value 6.02 times 10 to the 23rd. All right? Here's an example. Each of these has 1 mole. Notice, the mole is not always the same size. The sulfur takes up the most space of those. Copper would appear to be probably the least amount of space. But you'll also notice something else. Each one of these has a different mass, and we'll get to that in a little bit. All right, let's count with moles. All right, 1 mole is equal to 6.02 times 10 to the 23rd. What would 2 moles be? Well, you just multiply 2 times 6.02 times 10 to the 23rd, and you get 1.204 times 10 to the 24th particles. If you take 10 times 6.02 times 10 to the 23rd, you get 6.02 times 10 to the 24th particles. If you take a half mole times 6.02, you get 3.01 times 10 to the 23rd particles. Can't spell. Now, if you had particles and you want to change to moles, since you multiplied to go from moles to particles, you'll divide. So we would take this number divided by 6.02 times 10 to the 23rd, and that would give you 2 moles. If you have 6.02 times 10 to the 25th divided by 6.02 times 10 to the 23rd, you would have 100 moles. And 3.02 times 10 to the 25th particles would be 50 moles, if I did that right. So, that's good information to know. Now, on the periodic table, we find molar masses. Remember this picture that we just looked at? I said, notice the molar masses on here. The molar mass on the periodic table, you've already learned that 1 carbon atom, or the average mass of 1 carbon atom, is 12.001 AMU, atomic mass units. Well, fortunately, the mass of 1 mole is the same, only measured in grams. Scientists decided that they would make 1 mole equal to the number of particles in 12.00 grams of carbon. All right, so since 12 grams is equal to 1 mole, what would 2.5 moles of carbon be? Well, we'll take 12 times 2.5, which would be 24.5, 30 grams. 10 moles of carbon would be 120 grams. By the same token, if you have 60% 0.05 grams of carbon, 60 divided by 12 would be 5 moles. 240 grams divided by 12 would be 20 moles. 84 grams divided by 12 would be 7 moles. So now we need a tool that will help us to figure this out. And for that, we're going to use a mole map. What I would like you to do, please, is on the right-hand side, on this line, I would like you to write mass in grams. Okay? We just did this. If you know that you have 1 mole of carbon, you multiply it by the molar mass, which is what we get on the periodic table, and you get 12 moles. So if you're starting with moles and you're going to change to mass, you multiply by I'm having trouble talking, what we call molar mass. And that comes off the periodic table. If you have mass in grams and you want to go to moles, you divide by the molar mass, which is what we just did up there. Now this becomes something you can manipulate. If you're working a problem and it says that it wants you to find grams, you can put your finger on moles, follow the arrow, and the arrow tells you multiply by molar mass. If you're doing something that wants you to find moles and it gives you grams, again, you just put your finger on grams and follow the arrow to moles. So it's a manipulative. On the same token, if we are counting something, we're counting particles. That could be atoms, that could be molecules, that could be ions. If we know the number of moles, if I have 1 mole, I know I have 6.02 times 10 to the 23rd. So 2 moles, I'm going to multiply 2 times Avogadro's number. And if I want to go the other direction, if I know particles and I want to change to moles, I divide by Avogadro's number. Okay? This is your mole map. This will be important as we work problems. So let's try some problems. All right. The first question, what answer are you given? You're given moles, and it's asking you to find atoms. So if we hold up our mole map, it's given us grams, or moles, and it's asking us to find atoms. So we're going to go this way. Moles times Avogadro's number. So 12.7 moles of calcium, and I'm going to multiply it by 6.02 times 10 to the 23rd atoms in 1 mole. My moles will cancel, and I'll get atoms. Now, how do you do this if you have a calculator? All right, so the question was, too many things open on my screen. 12.7 times 6.02 times 10 to the 23rd. So I need to look at my camera. And what I'm going to do do this. I've got 12.7. Turn it on. 12.7 times 6.02. Now, what we're going to do for the exponent is we're going to use this second button and this EE button and put 23rd in there. And we get 7.65 times 10 to the 24th. All right, the next question, what information are we given? We are given atoms, and we are solving for moles of neon. So, again, 3.44, what we're given, times 10 to the 22nd atoms. I look at my mole map. I'm at this point now, starting with atoms, and I'm going to go back to moles. So I divide. And I'm going to use what's called the rail fence method. So I'm going to put it in the bottom so that my units will cancel. But if it's on the bottom of the rail fence, you just divide. All right, so we'll go back to the camera. So this time I'm going to take 3.44. Second E. Notice I don't put times 10 in. I don't do anything like that. I just let the E stand for times 10. Divided by 6.02 second E23. And I get 0.0571 moles. The next one asks for moles to ions. So I'm going to go back to my, well, here, first I'm going to set it up. So I'm going to set it up. I'm going to take 0.00561 moles of lithium ions, and I'm going to multiply times 6.02 times 10 to the 23rd ions in 1 mole. I'm going to go back to the calculator one more time. So 0.00561 times 6.02 second E23, 3.38 times 10 to the 21st, ions. All right, I'm going to skip to 5. How many moles of carbon are there with 24 grams? All right, now we're in a different boat. 24.02 grams of carbon, and we want to go from grams to moles. So now, instead of being on this side with particles, we're going to start with grams, and we want to go from grams to moles. which means we're going to need a periodic table. Let's see if I have it. All right. I thought I just popped up a periodic table, but apparently I didn't. All right, so periodic table, we zoom in. Carbon we see on the periodic table is 12.011 because carbon is not pure carbon 12. There's also carbon 14 and carbon 13. So what we're going to do is 24.02 grams of carbon, and we're going to divide by 12.01 grams in 1 mole, and we will then get 2 moles of carbon. The next one, how many moles are in 335 milligrams of barium? The first thing we have to do is change milligrams to grams. So divide by 1,000, you would have 0.335 grams of barium. Now we need a periodic table. Barium is over here, 137.328. And I'm going to divide again, 137.328 grams in 1 mole. Since we don't have any scientific notation, I don't need to show you the calculator. 0.335 divided by 137.328. And we get 0.00244 moles of barium. All right. Next question, moles of iron in 3.4 grams. 3.4 grams of, we're just going to pretend like that's iron and not iron oxide. And there, it did that weird thing again. So pretend like this is just iron. So, iron's molar mass is 55.85 grams in 1 mole. So 3.4 divided by 55.85 is 0.0609, or if we want to do significant digits, 0.061 moles of Fe.